I will present our ongoing work on efficient detection of multivariate correlations in both static and streaming data, or just multivariate similarity search for short. I think I have about 20 minutes for a full presentation, so let me just jump right in. So yeah, correlation analysis has been a quite common tool in exploratory data analysis for a lot of years now. For the people who don't know, correlation analysis involves looking at or computing the correlation values between variables in the data set. These variables are often vectors or time series even. And we do this to spot potential interesting interdependencies in the data that give us maybe hopefully some valuable insights. So up until now, these analyses have been mostly focused on measuring pairwise relations. So say correlation between two variables like you see here. However, recent work has now also shown the relevance of considering what they call multivariate correlations, which are correlations between 3 or even more variables. And I show an example of such a correlation here, where we measure the Pearson correlation between an aggregation of the temperatures at Sydney and Paris, and compare that with the temperature in LA. Now we call this specific correlation measure aggregated Pearson, or it's also called multi-Pearson in literature. But there are many more other variants of multivariate correlation measures. Now, the consideration of such more complex correlations with respect to the more pairwise relations has led to new discoveries in several fields. For example, it led to the discovery of a new weather phenomenon, where they found, by measuring the sea level pressures of different regions in the world, they found that the sea level pressure over the West Siberian plain was, for example, strongly correlated to the aggregated pressure levels at Darwin and Tahiti. And most interestingly is that this correlation could not have been found when only looking at these pairwise relations, because in this specific case, all the pairwise relations in this triplet here were quite low. But these multivariate correlations has also led to new discoveries in fields like, say, neuroscience, finance, medicine, genomics, just to name a few. Now, actually, the fundamental impediment or problem with finding these multivariate correlations is its computational complexity that quite simply comes from the number of unique combinations of time series in your data set that one has to consider. Quite specifically, if we would just run an exhaustive algorithm, it would have a complexity of n choose p, with p being the amount of time series you want to consider in a single correlation. So in the examples we've seen on the previous slide, we had a p of 3 because we were looking at triplets. Just to give you an insight of what the search space looks like here, just given quite a small data set of 1,000 time series, this algorithm would already boil down to iterating over about 500 million combinations, which would take about 7 minutes on a reasonably sized computing cluster. But if you want to also consider combinations of, say, 4 vectors, this number already increases to 500 billion, which would take about 1.5 days to compute. And actually, as a result, this method therefore could not be used for interactive exploratory analysis when simply using this exhaustive search approach. Now, there do exist some common solutions to battle such problems which have these combinatorial complexities, one of which is a priori filtering. However, this method will not work in this case because there's actually no guarantee that low correlations on small vector sets also imply low correlations on their supersets, simply meaning that if we have a combination of 3 vectors and that has a low correlation, still adding one vector to that, so making it a combination of 4, can actually result in a high correlation. And therefore, kind of the a priori filtering approach breaks there. Now, there do exist some algorithms which can prune some of these combinations and actually get better scaling than this combinatorial factor here, but they actually all rely on certain custom constraints or approximations, implying that they cannot guarantee to find all the interesting combinations of vectors that result in these high correlations. And to be more specific, past work has basically all used one of 3 strategies. So they either rely on a very specific problem statement, such that a priori filtering is actually possible. For example, some works required these subset correlations to be high in order to actually consider combinations of more vectors. Second strategy they use is they simply limit themselves to certain data types like binary data, or by creating an approximation algorithm without actually giving any correctness guarantees. Now, in contrast, our work actually aims at creating a more generic solution for multivariate correlation discovery that actually does not rely on these custom constraints. We also wanted to work with different multivariate correlations or aggregation functions. And we also wanted to extend it to streaming data, such that it could actually take place in any data analysis pipeline of a researcher that a researcher or a data analyst could use simply out of the box. Now, the result of this work is currently an algorithm named Correlation Detective, and its extension named CD Stream. And CD actually answers queries which involve extracting the most interesting multivariate correlations from a data set. And now this measure of interestingness is measured in the form of a query type, which many of you probably know. So we support both threshold queries and K queries. It also involves a correlation measure, which can be aggregated Pearson, like the example we saw in the first slide. But we also support aggregated Euclidean, which is essentially the same thing, but then with Euclidean similarity, which is a small transformation of Pearson correlation to measure the similarity between this set of vectors. And we also support 2 more specialized multivariate correlations, which are called multiples and total correlation. Now, together with this correlation and query type, a user can also define certain additional constraints on the result set, such as the constraint I talked about earlier, that the subset correlations need to be significant or insignificant for us to actually consider larger groups of vectors. And so this is essentially basically the summary of what we currently support. And as these query parameters are actually all variable, CD is the first generic solution to the multivariate correlation detection problem as we know now. Now, the intuition behind the algorithm is that many data sets actually often have some strong pairwise relations in them. So instead of just considering each vector or time series in the dataset individually, we hierarchically cluster our dataset based on these pairwise correlations, and we compute bounds on the possible correlation between clusters, instead of actually computing the exact correlation between individual time series. And this way, we can actually potentially prune a large amounts of combinations if the bounds on these combinations of clusters are conclusive, meaning they are either very, very low or they are very, very high. But let's take a closer look at the steps of the algorithm. So first we do some pre-processing. Certain similarity measures that we support, like Pearson, they require Z normalization of all the points in the data set. Next, we actually hierarchically cluster our data set on these pairwise correlations using multiple iterations of the k-means plus algorithm. And then starting at the root cluster, we start to compute we start to create these combinations of clusters and compute bounds on their multivariate correlations, given what we call a certain correlation pattern, which simply just means how many factors do we consider in the combination, and how if it's like a two-sided metric like Pearson, how many do we consider on the left-hand side and how many do we consider on the right-hand side. So we create a cluster combination given a certain correlation pattern, and we compute with some theory the range of possible correlations that we can get by creating a combination with the contents of these clusters. So in this case, we see that this correlation will be between 0.36 and 1, which basically means that any combination that we can create by just picking one element from each cluster and computing its multivariate correlation will be between these bounds. So if these bounds, which are actually based on the cluster radii and cluster centroids, if they're both below or above the threshold, we can make a conclusion on all of these combinations at once. And in case they're actually not conclusive, like it's the case here, we break the largest cluster into one of its subclusters, and we start to consider that combination. Now, this process actually continues until we only find these decisive combinations. And what's the decisive combination? Well, here you see that both bounds are below the threshold, so we can make a conclusion on all these combinations at once and simply just ignore them in this case because they're below the threshold. And now note that with really just a single computation, because computing these bounds is actually very efficient, we can now discard an extreme amount of possible combinations, and this is really where the pruning power of the algorithm comes from. So yeah, as I said, this process of breaking clusters, creating new combinations, it terminates when we only have decisive cluster combinations, which also means that we've essentially covered the whole search space. A last quick note on the algorithm is that actually these leaves in the cluster hierarchy, they are essentially clusters with only one element. So this means that this algorithm, worst case, still looks over all possible combinations if no cluster combination is actually decisive. However, in practice, we actually see that most of the cluster combinations are already decisive after 2 or 3 splits, making that we prune away about 99% of the whole search space. Now, the algorithm was evaluated thoroughly on its scalability and sensitivity to different data sets and input parameters, using both an exhaustive algorithm as a baseline, but also some of the previous state-of-the-art algorithms. Now note that because these state-of-the-art algorithms all had their own custom constraints and very specialized, only supported very specific queries, we had to construct some specialized experiments as well to account for these differences in assumption and result completeness. But yeah, for brevity, I will now only focus on the 2 main experiments in our evaluation. So with regard to scalability, we here compare to just an exhaustive baseline for different data sizes and these correlation patterns. So just a reminder, a correlation pattern is a combination of a correlation metric and the specified cardinalities on the left and the right-hand side of that correlation. So for example, here this MC13 refers to the multi-Pearson measure we saw before, allowing 1 vector on the left-hand side and an aggregation of 3 vectors on the right-hand side. Now, when we look at this plot, we see that CD is generally like 2 to 3 orders of magnitude faster than the exhaustive baseline, and it seems to scale in a more polynomial manner instead of this combinatorial factor you see here with a timeout already pretty early. Now, in the second experiment, we compared to the most prominent state-of-the-art algorithm, which actually supported the multipole metric with unlimited cardinalities. The state-of-the-art algorithm was a progressive algorithm. So to compare to it, I now show the percentage of result over time compared to this state-of-the-art. So we are correlation detective, state-of-the-art is common extended. And here we see that CD is actually able to find more results in around of order of magnitude less time, but maybe more notably, it's able to find more than 75% of the results in under a second. You can't really see it in this plot. I would need a log scale for that, but yeah, under a second, which actually indicates also big potential for a progressive variant of our algorithm with potential early stopping possibilities. Oh, let me get back. So just addressing some limitations of the algorithm, and an additional insight we found was that CD actually works best on data sets which include some very clear clusters in there, as the core of the algorithm, of course, is to exploit these strong pairwise correlations through clustering. So intuitively, the algorithm does not work very well on data that's random and difficult to cluster, because it will result in very loose bounds on these cluster combinations we saw earlier, which means that we actually need a lot of these cluster breaks in order to find a decisive combination. However, we actually found that all datasets we tested on were to some extent clusterable, and therefore never led to CD being outperformed by any of the baselines we compared to. Now, I'll start wrapping up a little bit. So again, please keep in mind that due to the time constraints, I had to limit this presentation to examples of a very specific query with the aggregated Pearson and threshold queries, and only on static data. But the paper we published at VLDB 2022, it actually also explains how we extend to streaming data as well, and how we handle these additional constraints, which did not appear in my examples. And also on top of that, it also includes a lot more experiments on these different query configurations and algorithms. But just looking forward a little bit with this project, eventually our goal with this project is to like generalize the methods I previously described and the theories that actually underlie those methods, in order to create like a unified system that will support any similarity measure, aggregation function, and constraints that comply to certain properties. Because from a lot of talks with other researchers and analysts, we see that every researcher actually has its own or requires its own similarity measure and has its own constraints. So we want to create a system that can actually support also custom measures and custom constraints, and make these methods really measure invariant, so to say. Also, additionally, we want to build an optimizer and a distributed executor that exploits this theoretical framework in order to actually derive efficient execution plans given the certain query of the user, so that we obviously can answer all queries with sufficiently fast. And I really believe that the latter goal should ring some bells in the audience here. So if you are interested in collaborating on this topic, or just want to share some ideas on query optimizer and distributed executors that may apply to this problem, yeah, feel free to contact me after this seminar. But yeah, from my side, that'll be it for now. Thank you for the attention, and I will now take the questions.